Hi, welcome to Math331, Lecture 15. What we're going to do today is, if there's time, some geometry, but we're really going to be talking about monovariants. So we have seen monovariants several times in class, and you have also seen them at other times in your life without realizing that you're seeing them. So did we do the zombie game in this class with the perimeter? Okay, so you've seen monovariants with the zombie game. Okay, we also did the Hershey bar game, right, where you break it up, and we saw the monovariant there, where the number of pieces is increasing by one every single time, so you know exactly what's going to happen. You've seen monovariants before. We actually saw them when we did the fundamental theorem of calculus. If we partition, and then we do a refinement, and then keep doing refinements, and keep doing refinements up to fill up 50 minutes. So if we keep going like this, the upper sum, what can you tell me about the upper sum in a case like this? What properties does it have? So we would have, u of 1, u of 2, u of 4, u of 8. What kind of sequence is that? Can't use words like it. So we're calculating the upper sum for our function on these intervals. As I make the partition finer and finer, each partition is from the previous by cutting each thing in half. What can you tell me about the values of the upper sums? Decrease. Can't say decreasing. It's almost decreasing.
Not increasing.
Not increasing. So it's non-increasing. Right. We really want to say decreasing, but we have to be careful. We have to say non-increasing. What if I give you the function that's constant? Then the upper sums are constant at every single time. The upper sums form a non-increasing sequence. This is a monovariant. It's moving in one direction. Similarly, the lower sums are non-decreasing. And then we show that the two of them converge to the same common value. So you've actually seen monovariants going back to calculus. Okay? So this is one place where you've seen it. We've also seen it in another place where we were doing geometry. We had the square root of 2 equals a over b. Right? This is probably the first real math proof you see in your career. It's either that or the infinitude of primes. Right? Or there's argument, you multiply all the primes, add 1. If the list was finite, you've either found a new prime or it's divisible by a prime not on your list. So what's the monovariant here? It depends on how you want to write the argument. But I want to form a sequence of numbers. So let's say I have a naught over b naught. That's my first rational approximation. Well, then what I can do is I can get 2 b naught squared is a naught squared. So what do we deduce?
A naught squared divisible by 2?
Yes.
And then
so the trivial thing is 2 divides a naught squared. The meat is the following. So what do we deduce if 2 divides a naught squared?
2 divides a naught?
Yes. So I can hear, I believe, Professor Silva across the wall. Yes? Other people hear Professor Silva? Thought I heard him. He and I actually wrote a paper about how to prove the following. If a prime divides xy, then p divides x or p divides y. This is a terrific property primes have. This requires, I think that's Professor Silva. So if a prime divides a product, then it must divide at least one or the other. Or both. This is the inclusive or. This is not the case if you have a number that's not a prime. So for instance, 12 divides 3 times 4, but 12 does not divide 3 and 12 does not divide 4. This needs to be proved. And so as a nice exercise, prove this rigorously. So we actually wrote a paper on how to try to prove this rigorously and how easy it is to accidentally assume something when you are proving this. If you look at the old Greek proofs of the irrationality of various square roots, you need essentially this. Now, you can prove it by brute force if I give you a specific number. If I want to show 2 divides a naught, I have 2 possibilities. I can write a naught as 2m or as 2m plus 1, and I would get a naught squared is 4m squared, or 4m plus 4 plus 1. And then we can see by brute force, this is odd, and that's not divisible by 2. And so in the special case when p equals 2, we can prove directly that if p divides a naught squared, then p divides a naught. What about if p is 3? If 3 divides a naught squared, well, 2m or 2m plus, well, now we would change this from 2m to what? If we want to work with the number 3. So if I want to have 3 divides a naught squared implies 3 divides a naught, I would have 3m or 3m plus 1 or 3m plus 2. And if you want to do it by brute force, we'd get 9m squared or 9m plus 6 plus 1, writing it like this, or 6m, thank you, or 9m squared plus 12m plus 4. And then you would see in all of those cases that the only one that would be divisible by 3 is the first. All right, so if we continue, 2 divides a naught, therefore we can write a naught as 2a1, and then we get 2b naught squared is 4a1 squared, therefore 2 divides b naught squared, therefore b naught is 2b1, and so we then get 2b1 squared is a1 squared, or the square root of 2 is equal to a1 over b1. And a1 is a naught over 2, b1 is b naught over 2. So if you want, you can view this almost as a monovariant. I start off with a rational that's supposed to equal the square root of 2, and I apply this argument, and I come up with a new rational where both the numerator and the denominator are smaller by a power of 2. And I just keep iterating and iterating and iterating and iterating. What will happen? So, where's the contradiction?
Don't you have the contradiction on like the first jump?
Well, I'm not assuming that they're relatively prime at this point. I'm just assuming I have a rational approximation that works. So let's assume we have a rational approximation that works. This then generated a smaller rational approximation.
There's always something that's more accurate? Or?
It's not more accurate. They're all equal to the square root of 2. They all have the same accuracy. So it's not an accuracy issue. So what is the issue? What is the mistake?
They get infinitely small.
They get infinitely small. I have an infinite chain of them. B naught is some finite positive integer. At every stage I have a positive integer. You cannot have infinitely many positive integers less than or equal to a given positive integer. So you might have heard of Famas' method of descent. This is really the method of descent, that you cannot have an infinite chain of positive integers that starts at a bounded number and continues downward. If you would allow negative integers, it would be fine. But the fact is, everything you have b naught is greater than b1, is greater than b2, is greater than b3. And since each one is a power of 2 less than the previous, you know you can't do this many times. You can do this at most, b naught plus 1 times. That's a much larger bound than you need. You really need like the log of b naught, but let's be safe. The process must terminate. And this leads to the method of descent. So this is one of the favorite ways of proving that you cannot have solutions to various things. So Fermat's last theorem is an extremely famous problem. This is the one where Famas remarks that he has a wonderful, remarkable proof, but sadly there's not enough space in the margins. He did, I think, eventually write down a proof in some special cases. And the method he uses in these special cases does not generalize, or at least we don't see a way to generalize it, to other cases. But what you can often do is you start off with a solution, and then you show that you could find a smaller solution. And if everything is parameterized with a positive integer, you can't do this infinitely often. And that will lead to the contradiction. So for instance, you can use it to prove that x to the fourth plus y to the fourth equals z squared has no non-trivial solutions. So why do I have to say non-trivial solutions?
They can all be 0.
They could all be 0, okay. Do a little bit less trivial than all is 0, but that's fine. That's a good start.
Y is 0 and
Yeah.
Z is x squared.
Yeah, y is 0 and z is x squared. And that will give you infinitely many solutions. I really don't want to be too proud at solving x to the fourth equals z squared. This is not an achievement worth celebrating. Now, when you're young, sure, you say, great job, you found a solution. Now, Famas' last term is normally not like this. It should be x to the fourth plus y to the fourth equals
4.
Yeah, it should be z to the fourth. If I can show that there are no solutions to this, is that good enough to show that there's no solutions to x to the fourth plus y to the fourth equals z to the fourth? Yeah. If I had x to the fourth plus y to the fourth equals w to the fourth, how should I view w to the fourth?
W squared.
Yeah, w squared squared. So if you remember from the last class, I think I had some fun by putting down n squared at one point, where there was really no reason to do n squared. This is actually time where it is useful. View w to the fourth as w squared squared, and now we can just take z equals w squared. So if we show that there are no solutions to this, then there are no solutions to this. This is actually a stronger statement that implies this one. And one way to do this is the method of descent. Assume you have a solution in the integers. Of all the solutions in the integers, choose one that has the smallest possible z. Generate a new solution that has a smaller z. Contradiction. Or if you don't want to argue by contradiction like that, you could just say, then you would have an infinite chain of solutions. You can show that whenever you have a solution, you can always find a solution with a smaller z. Well, you can't do that infinitely often. Something must be wrong. What's the only thing we've assumed? That there's an initial solution. Thus, there can't be a solution. It's the same thing over here. We assumed there was an initial solution to root 2 equals a naught over b naught. If that was the case, we had this nice monovariant. Okay. So this is just some explanation of places where you might have seen this before. What I want to do now is I want to turn to hopefully a new application of monovariants. I want to go back to Zeckendorf decompositions. Okay. How many of you are sophomores? Juniors? Okay. So for those of you who are sophomores and juniors, there's the opportunity of working at Small in the summer. And so I have had students do research projects with me on Zeckendorf decompositions. If this is stuff you find interesting, this is an opportunity for the summer. And in fact, if you work on these problems and do really well, I am one of the organizers of the next International Fibonacci Conference, which will be 2020 in Sarajevo. And so if you do really well, you have the opportunity of having all expenses paid to travel to Sarajevo. And if you do extremely well, I will even pay for you to come back. You always have to be careful and read the fine print and stuff. So have we done Zeckendorf decompositions? I think we've said a little bit about them. Right? So we've shown that every number can be written uniquely as a sum of non-adjacent Fibonacci's. And we did this with the greedy algorithm. Do people want to see the proof again, or are people comfortable with I can write a number as a sum of non-adjacent Fibonacci's?
Can you show how to write them as a sum of possibly adjacent ones, and then like the non-adjacent ones follow, I think, right?
Well, every number can be written as a sum of adjacent Fibonacci's. How would you do that? How would you write a number n as a sum of adjacent Fibonacci's?
Take the biggest one.
Nope.
Smaller?
No. Easiest way to prove that you can write it as a sum of adjacent Fibonacci's. Be trivial. Give me a decomposition that you know will work. You can use the same sum in multiple times.
Are just ones?
Yeah.
Yeah.
1 plus 1 plus 1 plus 1. Anybody want to guess how many ones we have?
And
ones.
Wow.
All right. So for a lot of things, you start with the trivial solution and see what you can do. As an aside, how many of you have heard of linear programming? All right. So linear programming. This is an aside. This is the advantage of a class like this: is we can have asides like this. You all know linear algebra, where I give you a system of equations and you need to solve them. In linear programming, you have more unknowns than equations, which means you have an underdetermined system. And typically there's a function you want to maximize or minimize subject to these constraints. If you ever have inequalities, you can actually get rid of the inequalities by adding some slack variables. So for instance, if I want x plus y to be less than or equal to 4, this is the same as x plus y plus z is equal to 4. Where I now just add that variable z to pick up some slack. So when you're writing things down, it's enough to assume that you just have equalities. You can always get rid of inequalities like this. One of the most famous linear programming problems is the diet problem. And so the diet problem is the following. I need 2 types of food. Steak? Anybody ever see the classic movie Meatballs? It's a camp movie from like the late 70s. So Bill Murray plays the crazy camp counselor, and he goes, the winner of tonight's mystery meat contest was Jeffrey, who guessed some type of beef. So I can see in some dining halls, I remember seeing some of the food at Yale marked grade D, fit for human consumption. They had to actually write on the boxes, you are legally allowed to serve this to the students. So meat and non-meat, okay. I need 2 types of nutrients or things we care about our food to have. Okay, we want it to have some fat, and what else? Sugar. If you truly believe that this is what matters, I can't wait until you have kids and you want to put them to bed. Please email me when that beautiful day happens. We want to make sure they have a sufficient amount of sugar and fat. Now, for the diet problem, what you want to do is you want to make sure you hit the minimum amount needed to live. You could actually put in additional constraints that you want to make sure you don't put in too much. A lot of times when you look at lab studies, let's give this rat or mouse 200,000 times the U.S. recommended daily allowance of whatever and see what happens to the rat. Right. You might want to put in some upper bounds and make sure you don't go too far. All right, so let's say you need at least 10 units of fat a day and at least 15 units of sugar a day. And 1 unit of meat will give you 5 units of fat, and 1 unit of non-meat will give you 1 unit of fat, and 1 unit of meat will give you 8 units of sugar, and 1 unit of non-meat will give you 12 units of sugar. And we'll say the meat, the cost of the meat is maybe $2 a unit, and the cost of the non-meat, well, we'll make the meat $3 a unit, and the non-meat is $2 a unit. So the question becomes, what is the diet that will keep you alive for the cheapest amount? If you are a dictator for a nation and you just want to make sure the peasants stay alive, this could be a problem you care about. Or you could be in a developing nation and you want to decide how should we allocate our agricultural choices to generate as much food as we can to keep the population alive. So the question is, how do you solve a problem like this? And it turns out, when you start plotting things, you end up getting various things. So if X is the amount of meat and Y is the amount of non-meat, both of these should be non-negative. You are not allowed to regurgitate food and then get actual credit back and money added back to you for throwing up some meat. All right? Reasonable assumption. Okay? And then you want to just plot what's going on. And so what you might have is a cost line like this and another like this. And to make sure that you have enough, this might be the fat line, this might be the sugar line, I don't care what they actually are. You have to be above this line, and you have to be above this line. So you find out you must be in this space like this. So I can erase the other parts like this. And so you have a nice complex polyhedra. And then you have some cost line like this, and this is your cost. And the cost is going to be, in this case, 3x plus 2y. And because it's like this, it's going to be a negative slope line. So this might be 3x plus 2y equals 100. As I move the cost down, the line shifts like this. Is it possible that the most optimal, cheapest diet is in the interior? No, you can always shift. So you now know immediately you've got to be on the boundary. So you've got to be somewhere from here to here to here to there. Great. And then if you hit over here, if you don't hit at one of the vertices, you can actually keep shifting. So now you know immediately there's only 3 points to check. And so you go from this incredibly hard problem to there are just 3 points to check. This is a very simple problem. You can make the problem significantly harder. I love teaching operations research. I hope to teach it next year. The reason I'm mentioning this is it is related to the wise ass of writing n as the sum of 1 plus 1 plus 1 plus 1 n times. There is something called the simplex method, which solves linear programming problems efficiently and quickly. If you've ever taken a computer science class, we love it when we get those words together. But it goes in 2 stages. There's phase 1 and phase 2. So the way phase 1 works is you assume you can do phase 2, and you use that to prove that you can do phase 1. And then using phase 1, you prove phase 2. So this seems circular. I assume phase 2, and I use that to prove phase 1, and now I use phase 1 to prove phase 2. The reason is you assume phase 2 works, and you use phase 2 not on the initial problem that you're supposed to study, but on a related problem. And it turns out it's a related problem which you can always prove there's a solution. So for instance, imagine you own American Airlines. What is your goal? Yes, your goal is to make money. Right? Your goal is not to fly planes. You own a movie theater. What is your goal? Maximize profit, right? It's not to show movies. So let's say you own American Airlines or movie theater and you want to make money. How do you do this? Well, American Airlines, hopefully it's by flying people. For movies, theaters, it's probably showing movies. But for movie theaters, and I've actually worked on problems with the movie industry, I'm happy to share some of the stories of the math behind this. You often make more money selling the popcorn and the reasonably priced soda to people than you do for actually the tickets. Which would you rather have? A movie with a lot of old people attending or a movie with a lot of college or high school kids on dates? You don't have to answer that out loud. You can try to figure out, if you're the movie theater, where do you think you're going to make more money? There are some movie theaters that show old movies for $1. And especially if it's a hot day, they just want people to come in and buy the concessions. And they'll make the money that way. So for a lot of these problems, what you need to do to get phase 1 to work is you need to know that there is an initial system that satisfies all the constraints. It may make you a horrible amount of money. You may go bankrupt if you follow this strategy. But you need to know that there is an initial solution that satisfies all of the constraints. That's what phase 2 is all about. Phase 2 is all about finding an initial solution. And then phase 1 takes an initial solution and moves to an optimal solution. If you run American Airlines, can you give me a feasible schedule that will satisfy all the constraints for your planes to fly?
Always be flying planes
No.
everywhere?
No.
Don't fly anything?
Don't fly anything. Can you give me a constraint for a movie theater that will satisfy, an initial solution for a movie theater that will satisfy all the constraints? Don't show movies. So it is amazing how often this trivial observation is actually valuable. And that's what allows us to do the linear programming. We do phase 2 for a very simple problem that's related, where we just assume we do nothing. And that's the initial solution that we then work on. So over here, we do something very trivial, but it turns out that's very valuable. It's the same for the movie industry. It's the same thing for these linear programming problems. Your constraints might be, if I'm showing a movie on this screen, I can't show another movie until the first movie ends and maybe some time for people to leave and clean up the theater. I can't show the same movie on 2 different screens simultaneously. You can have other additional constraints, such as I don't want too many movies ending at the same time because I don't want there to be too much traffic coming out. Or maybe I don't want too many movies starting at the same time because I don't want my ticket agents to be overwhelmed. And so there's a lot of these additional constraints you can put in. What was really killing the problem was the movie theater owner or manager did not want more than 20 minutes of delay between movies starting in the theater. He didn't want any gap so that if somebody showed up, they never would have to wait for more than 20 minutes. And this was just killing us in terms of runtime. And we finally told him, if every now and then you're willing to have a 25 or 30 minute wait, not often, but a few times, here's how much more money you can make. Well, it was really more of a suggestion than a requirement at that point. And he was quite willing to occasionally have 25 or 30 minute waits, given how much more people came in. And we actually were able to demonstrate this. And when they implemented this, they did get increased attendance. So if people are interested, let me know and I will share the papers with you. They're very readable. Over here, this is something to start with. And in fact, this is the Fibonacci game we played, where you start off with N1s and you apply various rules to combine things. So this goes back to, can you start off with a decomposition and pass from this to the Zeckendorf decomposition, where you have everything that's non-adjacent? And the answer is yes. That's the Fibonacci game. That was Alyssa Epstein's senior thesis last year. This is the game I showed where the goal was to beat my daughter Kayla. We know that the second person always has a winning strategy unless n equals 2. Because if n equals 2, there's only one thing you can do. You have 1 plus 1 and you have to just combine that to the 2. So it's really not fair to play 2. There's only one move possible. All right, so how is this useful? So the Zeckendorf decomposition, we know you can always get to it. So let's say we have the Fibonacci 1, 2, 3, 5, 8, 13, 21, 34, 55. And let's take, somebody give me a number that's less than 89. And at least 20. 88. 88, thank you. You're making me work for it, huh? So 88 is 55 plus 33, right? And 33 is 1 less than, I know exactly what this is going to be. It's going to be 55 plus 21 plus 4, plus 8, no, 12. Plus 12. Because it's got to be 1 less than this, right? So I have to keep going as much as possible. So it'll be 55 plus 21 plus 8, and then it should be 1 less than 3, should be, 1 less than 5, so it should be 4, yep. And then it will be 55 plus 21 plus 8 plus 3 plus 1, and we're now done. So we'd actually get 55, 21, 8, 3, and 1. You gave me the longest possible one to do. As an aside, do you all know the 3x plus 1 problem?
That was, wasn't that an Euler?
It could be one of the Euler problems.
The call-out?
The call-out sequence?
Yeah.
If your number is odd, multiply by 3 and add 1. If it's even, divide by 2. So, as an aside, an plus 1 is 3an plus 1 if an is odd. it's an over 2 if an is even. So this is called the 3x plus 1 or the Collat's problem. My two favorite quotes about this is first by Kakatani. I would travel around the country visiting math departments, and whenever I talked about this problem, people would say, oh, that's not so bad, and they'd spend about a month working on it in frustration. And eventually people said that this was a Soviet conspiracy to slow down American mathematics. Any Star Trek Next Generation fans? There is a Star Trek Next Generation scene where we almost do something similar to try to stop the evil Borg by giving them a problem like this. The other quote is by Paul Erdős, who said mathematics is not yet ready for problems like this. It is conjectured that no matter what positive integer you start with, eventually the sequence cycles to 421, 421, 421 for all time. If you ever want to be painful to somebody, give them a starting seed of 27. Of all the small numbers, this one has an abnormally large iteration time. A lot is known about this sequence and about, on average, how long it should take for various things to happen. So, I knew as soon as you gave me 88 that you were going to make me work for today's lecture. But, anyways, we have personalized midterms, so it's not a real problem. So here's the Zeckendorf decomposition. How many summons does this have? When I decompose 88, how many summons? 5. This is not a challenging 1, 2. I don't care how you do it. And in fact, you can even do it on one hand. 5 summons. But now, this is a very special 5 summons. They can't be adjacent, and you can't have anything repeated. What if I say I'll allow you to have repeated summons, and I'll allow them to be adjacent? There's other ways to get to 88. Can anybody do it with fewer than 5 summons? So can anybody give me maybe another thing we could try?
234.
Yeah, let's try 2 34s. 34 plus 34 is going to be 68. So we need 20. Right? Damn, can't quite use that 21. I'm sorry.
Could be 13 plus 5 plus 2.
So 34 plus 34 plus 13 plus 5 plus 2. So this is already enough to prove a theorem. The Zeckendorf decomposition will not always be the minimal number of summons. So I was a postdoc at the Ohio State University. But what is still fair game is that maybe it is a minimal decomposition. And that actually turns out to be a theorem. There is no decomposition of a number into Fibonacci summons that uses fewer terms than the Zeckendorf. So what you do is you start off with an arbitrary decomposition, and you construct, what do you think you construct?
A Zeckendorf?
Well, you're going to start off with some decomposition, and then you're going to move through decompositions and end up in the Zeckendorf decomposition. And to each decomposition, you're going to associate a number. What do you think will be true about that number?
Non-increasing.
It'll be non-increasing. You'll have a monovariant. So that's one way to prove this, is that as you pass from any decomposition to the Zeckendorf decomposition, you end up decreasing or staying the same at every step. And since you end in the Zeckendorf decomposition, nothing can have fewer summons than this. You start off with any decomposition and then show you can end up with a Zeckendorf. And so all you have to do is show that all the legal moves never increase. Never increase. So what you could do is you could combine 2 adjacent terms, or you could take a double term and split it. So I will leave this as a problem for you to pose and ponder. So I've recently proved massive generalizations of this with some summer RU students. The paper we were just finally told was just published like a day or two ago. And we have massively generalized, not just to the Zeckendorf and Fibonacci's, but to more general recurrence relations. And we've actually come up with conditions. If I give you a recurrence relation, what must be true about the recurrence relation for the generalized Zeckendorf decomposition to have the fewest number of summits? So I will just give this to you as something to ponder now. It might even be one of your homework problems, is to prove that of all the decompositions, nothing is less than Zeckendorf. And the idea is to associate a monovariant. Now you will notice that I have explained to you what a Zeckendorf decomposition is, and I've explained to you what the rules are, but what haven't I given you? I'm sorry? What do you mean by a method? You're close.
How to move between decompositions?
Well, the way to move between the two compositions is you take two adjacent Fibonacci numbers and combine them to the next one. So you take maybe 8 and 13 and combine that to 21. Or you take maybe two 34s and split that up into a 55 plus a 13. So I've given you the moves to go from one decomposition to another. And I've told you you should be able to associate a monovariant, which is non-increasing. What have I not given you? That's the hardest part of the problem.
Proof that you always end up at the Zeckendorf?
If you are not, so that that is true. That's not horrible to prove. If you ever have things that are adjacent, then you could combine them. If you ever have things that are double that you can split, you just need to show that the process will terminate. So you are right that you need to prove that it terminates. But when we did the zombie problem, what was the hardest part of the zombie problem? Yeah, getting the monovariant. So when you're doing this, I haven't told you what the monovariant is. There is a monovariant if you make a good choice. The choice I initially made is actually not the best choice. Alyssa came up with a better choice than the one I was using. The one I used works, but her one works better and cleaner. This is almost where the art comes in, is figuring out what to look at. I will risk invoking your memories of Calc 3 and sequences and series, or maybe you did this in real analysis. Convergence tests, right? I apologize, but math is cumulative. Who remembers their convergence tests? And by remember, I just mean be able to give me a name. What are the names of convergence tests?
The ratio.
Ratio test is up. This is like Family Feud. Show me ratio test. How many of you have watched Family Feud? How many of you have never seen Family Feud?
I think I've played the online version.
Okay.
Studying.
I will try to send my favorite clip from Family Feud history. So if you win, you go to fast money and two people go up and each person gets 5 questions. And if your team gets 200 points, you win $10,000. And so one time, the first person by herself got over 200 points. It is extremely hard for one person to do that. So the host said, do you want to have some fun with your sister? Sure. So we'll tell your sister you got 13 points or something like that. And then the host just asks the most ridiculous questions. And you just see the sister. So I'll send you the clip. He's just having so much fun with that. Oh, it was a lot of fun. Ratio is up there. So give me another answer. I'm sorry? Comparison test. Comparison is up there. There's at least one more you should be aware of.
Absolute value.
What's the absolute value test?
If the absolute value converges, then if the absolute value of each individual term sum of those converges, then the normal sequence converges.
Okay, so that's basically, if a series is absolutely convergent, then it's conditionally convergent.
Yeah.
Sure, I'll put that up there. Absolute convergence implies conditional convergence. But there's at least one more that you should be aware of. Not the ratio test, another one that begins with an R.
Root.
There you go. I was going to say, what are the big letters you can have? Root test. If you are not able to remember this does mean that there are some either gaps or repressed memories from your previous classes here. You should know about the ratio test. You should know about the root test. There is the squeeze theorem. Something's done. Why am I mentioning these? Why is Professor Miller mentioning? So one reason is I do want to review some of the gaps in your math background. This is really the only class at Williams where we can do that, where if there's a gap, we can fix it. If people want, I'm happy to prove why these work or talk about these. Email me and let me know. We have that freedom. Which of these tests are easy or hard? Well, the root test is you look at the limit as n goes to infinity of an plus 1 over an in absolute value. And if this is less than 1, it converges. If it's greater than 1, it diverges. And if it equals 1, you have no information. Is this coming back to you now for the ratio test? Somewhat. The root test is similar, except instead of taking ratios, you take the nth root. The comparison test is much easier. So for instance, if you have, if say 0 is less than or equal to an, less than or equal to bn, and cn is less than or equal to an, then if the sum of bn, make sure this, if the sum of bn is less than infinity, that implies the sum of an is less than infinity, so an converges. And if the sum of cn equals infinity, that implies the sum of an equals infinity. So if my sequence of positive numbers is bounded by a sequence that converges, it converges. If it's greater than a sequence that diverges, it diverges. Of these tests, ratio, root, comparison, which do you think is the easiest test to use? Or which do you think is the hardest to use? Would you rather do the ratio test or would you rather do the comparison test? Okay, why comparison?
Assuming that you know the behavior. I guess there's no guarantee.
Well, so you need to know what Bn is and what Cn are. I just give you the sequence An.
Oh, I see.
Right?
Yeah.
So if I just give you the sequence An, you need to be clever and you need to think and figure out what is Bn and what is Cn. For this, you just need to take the ratio and be able to do the algebra. This doesn't mean you can do the algebra, but this is far more difficult. I'm just being honest, okay? Algebra can often be hard. And you might even get 1. And if you get 1, then it's no information. If you take the series 1 over n or 1 over n squared, if you try to do the comparison test, you might be able to get it to work, but the ratio test will not detect that 1 over n diverges and 1 over n squared converges. For the comparison test, you need to be clever. You've seen this before. If I give you a quadratic to factor, what's your first thought to factor the quadratic? Say x squared minus 7x plus 12 equals 0.
X minus 3x minus 4.
I actually got x minus 4x minus 3, but it's close enough. How did you do that so quickly?
Think about numbers that.
Think about numbers.
-7.
Right. Everybody's comfortable thinking about numbers like this. What if I gave you x squared minus 7x plus 11 equals 0? You think about it for a while, you realize 11 is prime, and you start cursing, and then you realize it's not going to be nice. What do you do in this case? Quadratic formula. Is the quadratic formula bad? No, and again, you have to look at the greater scheme of things in life. If I'm asking you to do negative b plus or minus square root of b squared minus 4ac over 2a, that's not bad. It's mechanical, methodical. You know you can just grind through it. Which is faster, to use the quadratic formula for this, or to just notice that it's 4 and 3? Just notice it's 4 and 3. I view this as the comparison test. If you can see what to do, it's much faster. But if you can't, then you can always fall back on the quadratic formula and you have this mechanical procedure that will work. It's the same way with the monovariants. If you see what to use, it's not so bad. If you don't see, it's extremely painful. And then the question becomes, how do you find the right monovariant? How do you have that divine inspiration? How do you have that, I'm intelligent? What was the word? Genius? How do you have that moment of genius, that flash of inspiration? To notice that, the monovariant I want to use is the following. That's what makes these problems hard. The more problems you do, the more experience you have, the more you might get a sense of this is a good thing to use for the monovariant. I think having this at 90 degrees was causing it to go up and down. Okay, so the difficulty is figuring out what is the right monovariant. So I'm not going to tell you for now. I'm going to let you try to think about this for Wednesday. What would be a good monovariant to try to use to prove that as I move from decomposition to decomposition, I never increase the number of summons. As I move to the Zeckendorf decomposition, the number of summons either always stays the same or goes down. And as long as I can prove that everything will eventually end in the Zeckendorf decomposition, I win. Alright, so we will talk more about this on Wednesday. We have not gone into the magic wand game. Does anybody want to say anything about the magic wand? Yes.
I think I can do it in 3.
You think you can do it in 3?
Yeah.
I can do it easily and countably many times. The question is, can you first prove that you can do it even incountably many times? And then can you do it in a finite number, then can you do it into 3? And so I believe I can do it in 3 as well. Can you do it explicitly? Okay. Excellent. Anybody else have other numbers? We know it can't be 1. So the only question is, can you prove it can't be 2? So can you prove that with a magic wand that kills all points of rational distance, that 2 tosses can't be enough? That shouldn't be too hard to prove. How do you prove 2 tosses can't be enough? Well, we're out of time. So I will leave you in suspense.